In the Ohm's Law lab, you originally graphed voltage on the x-axis because that was your independent variable, and you originally graphed current on your y-axis because that was your dependent variable. And I had you switch the axes around so that you could see more easily what the slope means, but I'm going to go back and change these notes to put in the original labels. So voltage really is our independent variable because that was what we changed. You put different numbers of batteries in the battery holder. And current, which is the letter I, in amps, was really our dependent variable because that changed as a result. And you should have gotten a direct relationship when you graph that. The slope of that line meant the reciprocal of resistance. So slope means, and the y-intercept should be 0. So in other words, there is no y-intercept, and it just means that when there is no voltage, there's no energy to give to the charges won't move. So when we put those things together, we get a relationship that's more commonly known as Ohm's Law. Our y variable, current, is equal to our slope, 1 over the resistance, times the voltage. So we can affect the current by either increasing, or we can increase the current by increasing the voltage, or by decreasing the resistance. We're going to go through a few quick examples using Ohm's Law and putting it to use, and then we'll learn what power is. So an electrical device with a resistance of 3 ohms will allow a current of 4 amps to flow through it if a voltage of this many volts is impressed across the device. So we know that current is equal to voltage divided by resistance. We know the current is 4 amps, and we don't know the voltage. We know the resistance is 3. So if you solve multiplying both sides by 3, the voltage that would be required is 12 volts. Next example, when a voltage of 120 volts is impressed across an electric heater, a current of 10 amps will flow through the heater if the resistance of the heater is. So again, I equals voltage divided by resistance. The current is 10 amps. The voltage, which is standard voltage in the US, is 120 volts. And we want to know what the resistance of the heater is. And I get 10R equals 120 by multiplying both sides by R. And then R is equal to, divide both sides by 10. I get 12 ohms. And third example, a flashlight is powered by 3 volts, so basically 2 AA batteries, and it uses a bulb with a resistance of 60 ohms. What's the current flowing through the flashlight? So current is equal to voltage divided by resistance. So the current is 3 divided by 60, which is 0.05 amps. So just using Ohm's Law, it's a pretty simple equation, and really these are all just kind of plug and chug problems. Next, we're going to take a look at what power is and how to calculate how much power is consumed in electric. So we've actually talked about power once earlier this year. Power is the amount of energy, it's the rate of energy usage, the amount of energy used in 1 second. And we've also learned that the symbol for power is P, and the units of power are watts, which are abbreviated as capital W and are defined as a joule in every second. So power's energy divided by time. We also know that current is charge divided by time, and voltage is energy divided by charge. So if we take current, which is charge divided by time, and multiply that by voltage, which is energy divided by charge, we get charges canceling out, power is equal to energy over time, which is what we just said. What we did here is we took current multiplied by voltage. So power, therefore, is equal to current times voltage. So we've got a new expression, we haven't redefined power. It still means energy used every 1 second, just like it did back in chapter 7, but we have a new way to calculate it using current and voltage so we can find out how much power is consumed, how quickly energy is consumed by different electrical devices. So we've got a couple of examples using the power calculation for electric circuits. This says calculate the resistance and the current of a 1,500 watt electric hairdryer plugged into a U.S. household outlet with a voltage of 120 volts. Well, we just learned that power is the same as taking current times voltage. We know the power consumed by this hairdryer is 1,500 watts. We don't know the current that flows through this hairdryer, but we do know we're going to plug it into an 120 volt outlet in the US. So if I do some algebra here, divide both sides by 120, I find out that the current consumed that flows through this hairdryer is 12.5 amps, which should probably only have two significant figures because that's all we had in our problem, so 13 amps. It also asks us the resistance. Well, we still have at our available to use Ohm's Law, which says current is related to voltage divided by resistance. We just figured out the current is 13 amps. The voltage is 120 volts. So we're going to solve that for resistance. 13, multiply both sides by R, so 13R equals 120. Divide both sides by 13, and the resistance offered by the hairdryer must be 9.2 ohms. We got a second example. The box on a table saw indicates that the amperage at startup is 15 amps. Determine the resistance and the power of the motor during this time. Well, we know that the voltage is going to be 120 volts because we're assuming we're using it here in the US. And we know that current is equal to voltage divided by resistance. So we know the current is 15 amps. The voltage is 120 because we're using a wall outlet. So we're going to solve for R. 15 R equals 120. And so R, the resistance, is 8 ohms. We also were asked to calculate power. Power is equal to current times voltage. So the power consumed, the amount of energy consumed every second at startup is 15 amps times 120 volts, which gives us 1,800 watts, or 1,800 joules in every second.